In this video, we're given a question that demands of us 1. To determine the intercepts the curve makes with the coordinates axis. 2. To find the turning points of the curve, distinguishing between them. And the third part of the question, we are expected to sketch the curve. So let's go ahead with the solution. Now, this is a cubic polynomial or a cubic function, and generally their domain is a set of all real numbers, which means that any value of x substituted in the equation will produce a valid outcome. It is also important to note that for a polynomial function with integral coefficient, a leading coefficient of 1, and a non-zero constant term, the zeros of this polynomial must be the factors of the constant term. So the factors of 9 is given as, so what we are going to do is that we are going to test the roots on this polynomial. In other words, we are going to plug them into the polynomial until one results in 0. So let's consider the first one and substitute +1 into the function. So we're going to get and that gives us 0. Now, if +1 had not given us 0, we would have gone ahead with -1. If -1 had not given us 0, we would have gone ahead with +3, -3, +9, -9, until one of them results in 0. And because +1 has resulted in 0, it means x is equal to 1 is a root. And if x is equal to 1 is a root, then it means x minus 1 is a factor. So we can break down this polynomial into its factors as such. Now, what do you think this factor is going to be like? Because this first factor is a factor to the degree 1. And so this factor here should be a function to the degree 2. And for that matter, this factor here should be a quadratic function, which is going to have the general formula. So how do we determine this quadratic function? Let us apply the simplified method of polynomial long division. So we have this factor, and we have the function here. Now, the function is the dividend, and this factor here is the divisor. So what we're going to do is that we're going to focus on the first term of the dividend and the first term of the divisor. So we're going to divide this first term of the dividend with the first term of the divisor, and we are going to get, then we're going to multiply this quotient with the divisor, and the product, we write it here. Then we're going to subtract the product from the dividend, and we're going to get, and we're going to bring down the next term. Then the same procedure is going to repeat itself. We're going to divide the first term of this expression over here with the first term of this divisor, and we're going to have, and we're going to multiply this with the divisor. Then we are going to subtract it. We're going to repeat the same procedure. We're going to divide this first term of this expression with the first term of the divisor. And we're going to multiply this number with the divisor. And this quadratic equation that we have here, we'll plug it in over here. So we're going to have we will simplify it further. And we're going to have so in this factorized form, we can now go ahead and answer the first part of the question, which is to determine the point at which this polynomial cuts the coordinate axis. So at the y-axis, we put x is equal to 0. So it would mean that wherever that we see x, we put 0 there. So we're going to have, when we substitute x as 0, we're going to have so y will become -9. So it means that the curve cuts the y-axis at the point 0, -9. Let's consider this point as point A. Now, at the x-axis, we put y is equal to 0. So it means that either x minus 1 is equal to 0 or x minus 3 is equal to 0. X minus 3 is occurring 2 times, and so we just ignore one of them. So it means that x is equal to 1 or x is equal to 3. So it means that the curve is cutting the x-axis at 2 points. First of all, at the point 1, 0 and 3 is 0. And let's consider this point as point B and this one as point C. So this is the first part of the question where the curve is cutting the y-axis at the point 0, -9, and it is cutting the x-axis at the point 1, 0 and 3, 0. Now, for the second part of the question, we are asked to find the turning points of the curve, distinguishing between them. So let's go ahead with it. Now, the second part of the question, we have our curve here. Now, to determine the turning points, we would need to determine the first derivative of this polynomial. So dy dx is equal to 3x squared. Now, at the turning points, dy dx is 0. So we're going to equate this equation to 0. and find the values of x which satisfies this equation, and we're going to apply the quadratic formula. For a quadratic equation, generally we have in employing the quadratic formula, where s can be determined by using where a is equal to 3, b is equal to -14, and c is equal to 15. We're going to plug in the values to determine the values of x. So we go ahead and simplify. Fourteen squared is 196, and this one will give us 180 over 6. So we have 14 plus or minus 196 minus 180 is root of 16. Then we have 6 here. So we're going to have x. So we're going to have x is either equal to 10 over 6 or x is equal to 18 over 6. X is equal to either 5 over 3 or x is equal to 3. X is approximately equal to 1.67 or x or 3. What this means that at this point, the curve will be turning at the point x is equal to 3 and also at the point x is equal to 1.67. So here it means that x is equal to either 3 or x is equal to 1.67. Now, when x is 3, what would be its y value? Because we need to determine that point. And when x is equal to 1.67, what will be its corresponding y value? Because we need to determine the coordinates of the turning points. So when x is 3, y is equal to 3 into brackets So when x is 3, this will be 27. This is 9, 45, 9. So y is equal to 27. So y is equal to 0. So the point 3, 0 is a turning point. The same point 3, 0 cuts the x-axis. So at this point 3, 0, the curve will cut the x-axis here. At the same time, at this point 3, 0, it's going to be a turning point for the curve. So what if the x is also 1.67? At this point that the curve is turning, what is its component y value? And so let's substitute this value of x into the original equation to determine its y component. So we're going to have so we're going to have a y value of 1.185, approximately 1.19. So the other turning point of the curve is 1.67, 1.19. Now let's consider this turning point as C also, because it is the same point which cuts the x-axis. And so let's consider that point as C also, and let's consider this point as point D. So at these points, so at the point C and D where the turning occurs, which one is the maximum turning point and which one is the minimum turning point? To determine that, we're going to find the second derivative of this expression over here. So let's go ahead to determine the second derivative of this expression in order to be able to differentiate between the turning points, which one is the maximum turning point and which one is the minimum turning point. So dy dx is given by 14x plus 15. And so the second derivative is given by, so when x is equal to 3, we have, should give us 4. And when x is equal to 1.67, we're going to have this implies we're going to have negative 3.98. So because the second derivative at the point is equal to 3 gives a positive value, means that this turning point is the minimum turning point, and the point where x is equal to 1.67 with the second derivative giving a negative value, the maximum turning point. So we have here the minimum turning point, and this is the maximum turning point. So having determined the points the curve cuts the axis, that is the y-axis and the x-axis, and having also determined the maximum and the minimum turning points, we can now go ahead with the third part of the question and sketch the curve. The curve cuts the y-axis at the point A, which is 0. So here is -9. At the x-axis at the point B, which is 1, 0. And at the point C, which is 3, 0. And at the point D, which is 1.67, 1.19. So we have these points, this, and that. D is the maximum turning point, and C is the minimum turning point. So we're going to have a curve in the form So that is the curve. So when we are asked to sketch a curve, first of all, we would have to determine the points that the curve would cut the axis. We would also have to determine the points at which the curve will be turning. In this particular case, it's turning over here, and at the point 3 is equal to 0. And then also determine of the turning points, which one will be the minimum point, here as in C, which is the minimum turning point, and here as in D, the maximum turning point. So that is the end of my video. Thank you very much for watching, but keep watching.